Welcome back, everybody. Um, Here we are on we're on week 4. And time is flying by, and it's nice outside. So what's there to complain about? So I'm going to go through and we'll go through the little quiz that we did last week for the um, review of the quiz from last week. We have question number 1. HMA pavements are typically made of what percent asphalt binder? And the correct answer would be 5%. It's usually around 5%. Maybe it's 5.5, 4.5, something like that, but it's usually around 5% asphalt binder. Number 2, asphalt binder we use today is made by burning crude oil or coal. That is actually false. What we're doing is we pull all the other fuel oils out of the crude oil, and that's where we end up with our asphalt. So we don't burn it. We don't do anything to it other than just separate out the different size hydrocarbons in there, because gasoline hydrocarbons are much smaller, shorter than what the asphalt hydrocarbons are. The asphalt hydrocarbons are much longer than other fuels. So we pull those lighter ones out, those smaller hydrocarbon chains, and then what we're left with is asphalt. Number 3, which of the following statements about viscoelastic material are true? A, at high temperatures, the material is more elastic. No, that's false. The high temperature becomes less elastic. B, has qualities of both a fluid and elastic material. Hey, I think we have a winner with B. And C, it crystallizes at room temperature. That is incorrect. So the right answer is B. Number 4, the viscosity of asphalt binder decreases at higher temperature. That is true. Viscosity, if you recall, is a fluid's resistance to flow. So the higher the viscosity, the harder it is to pour. So when we heat up the material, it gets softer and it pours easier. So number 4 is true. Number 5, cold feed bins. Well, this is a multiple choice. A, meter different aggregates onto a conveyor that delivers them dried and heated. No, that's not right, because this is where the material first enters the mix plant. So those aggregates are cold, or whatever the temperature is outside, and wet. B, sieve material into particle sizes prior to being mixed. That's incorrect, because that's more of what the screen decks do. C, dispense hot asphalt directly onto trucks. That's not correct, because this is just the aggregates that are feeding into the plant. D, contain the final aggregate blends of aggregate used for the HMA production. That is correct. But remember, cold feed, that's just where the material enters the plant. And so it's whatever temperature it is outside and however wet it is, depending on how much rain we've gotten. And so the correct answer to 5 is D. 6, silos. A, meter aggregate onto the conveyor to be dried. No, that's not correct. B, sieve material into particle sizes prior to being mixed. Again, that's incorrect. Store hot aggregate before it's mixed with asphalt binder. No, we don't store aggregate in our silos, but D, we do store hot mix asphalt for several hours. So when you drive by one of these mix plants and you see those big round cylinders, those are silos that are storing hot mix asphalt. And so the correct answer to 6 is D. Number 7, hot bins. Meter aggregate onto a conveyor belt to be dried. No, because the material in a hot bin has already been heated and dried, so we don't have to worry about that. B, are found in batch plants, but not in drum plants. Well, that is true. Hot bins do exist on batch plants, but not in drum plants. And then C says dispense hot mix asphalt directly into trucks. That's incorrect. And D, store hot mix asphalt for extended periods of time. That's a silo. So the correct answer is B, are found in batch plants, but not in drum plants. Number 8, aggregate only needs to be warm, but moisture may be present in the particles before mixing with liquid asphalt binder. That is false. You need to get rid of that moisture before you add the asphalt binder to it. So 8 is false. Number 9, which of the following statements about silos is incorrect? Silos are heated. They are, so that's not the answer to this one. Material may be stored in silo for an unlimited amount of time. No, That one is incorrect because the longer we hold that material in the silo, the more it ages. And the more it ages, the more brittle it becomes, the more likely it is to give you problems later on. And then C, D, and E are incorrect. Silos are necessary for drum plant operation. They are required. They're optional for batch plants. And aggregate segregation can occur in silos. So the correct answer to number 9 is B. And number 10, identify one false statement about the difference between drum plants and batch plants. Drum plants can produce material with more wrap content. Well, that's true. Drum plants typically produce more material than batch plants. That's true. C, it is more difficult to switch between producing multiple mix types throughout the day using a drum plant. That is true. Batch plants have hot bins. Drum plants do not. That is true. E, batch plants don't require dust collection systems. That is false. You do have to have a dust collection system on whether it's a drum or a batch plant. So E is the one answer that is not correct. So hopefully you guys did well on that little quiz and all is good. And then we'll move into the what we're going to talk about today, unless somebody has any questions. So we're always welcome to ask questions. We encourage it. So don't ever hesitate to just unmute yourself and jump in. Today, we're going to be talking about paving mixtures and a little bit about placement as well. So this is what we're going to talk about this week. We're going to talk about some temperature, some random sampling, some loose mix sampling, quartering, compaction, and some stuff we can do in the lab. So when do we take temperatures? Well, we talked about the importance of temperature during production last week. We also need to check it out in the field, because if the material arrives really cold out in the field, you're not going to be able to compact it very well. And if you can't compact it, it's going to allow a lot more air voids in that material. And those air voids are going to allow the oxidation to occur, and you're going to end up with a pavement failure. We want to check the temperature at the back of the screed as the material comes out from underneath the paver itself, because we want to make sure because if it's not warm enough there, it's never going to be warm enough to be able to actually compact it with the rollers. And each mix itself is specific to the temperature that it likes to be compacted at, I should say. And so each roller, we're going to position them to try to optimize so that we can get the best compaction we can with each roller, because the idea is to maximize the effort that you get with each roller so that there you get good density. And then we also need to keep track of the temperature so we can open the road to traffic, because if the material is still too hot, when you open up the road to traffic, vehicles going across that are going to start digging into that pavement, and they're going to start pushing and shoving that pavement around, and it's going to be problematic. So we need to keep track of our temperatures to make sure that we're doing a good job. And so there's many places out in the field that we're going to look at that. And we also need to look at the temperature of what we're paving over, because if the paving over material that is really cold, that cold base material that's already out there is going to suck the heat out of there very quickly as well. So again, temperature is very, very important to asphalt. And so we need to make sure we keep track of that throughout the production. And so you would take temperatures so that you can see this guy over here on the left. He's taking temperatures as that material is coming out of the back of the truck using an infrared temperature gun. And then we have 3 general zones when we're actually compacting it. We have the breakdown zone. This is close to the paver. And so this is where the material is the hottest. And this is where you get the most density. We then have an intermediate zone where we're going to get a little more density out of it. And then we have what's known as the finishing zone. This is where we're just trying to iron out any marks in the pavement, things like that from the actual construction, so that at the end of the day, when it cools off, it looks good and it looks nice and uniform and that kind of thing. So the breakdown zone, this is where the temperatures are the highest. This is where you're going to get the most density. You'll get some additional density here, and you'll get very little density back here in the finishing zone. So the further away from the paver you go, the more the material cools off. The more it cools off, the harder it is to compact that material. So there's different ways we can measure temperature. One of the things that we can use is an infrared temperature gun, which is this guy right here on the right that I just circled, but that only measures the temperature of the surface. We have also what are known as temperature probes, where we can actually stick it into the material. And here we're actually measuring the temperature inside the pavement, whereas the infrared only measures the surface. And so things that are going to affect the amount of time we have to compact this material is how thick that mat is. The thicker the paving mat is, the thicker the material is coming out from underneath the paver, the longer it's going to stay warm, just because there's more of it. Whereas if you go really thin with that, it's going to cool off very, very quickly. And so therefore, that's one thing that comes into play, is how thick are we placing that pavement material? What's the air temperature? The air temperature obviously is going to cool that pavement off as it's sitting there. And so that's a temperature we need to keep track of. The temperature of the ground, kind of talked about that already, but if the ground is really cold, that pavement's going to cool off very quickly as the heat is sucked into that ground. And also, what's the temperature of the mix when it's actually delivered to your job site? And so these are things that as a QC technician, you would be keeping track of, because in July, the temperature of the ground probably isn't that critical because it's going to be as warm as it's going to be. Air temperature is probably not quite so critical, but we still want to make sure that the material is being delivered hot enough. And we also want to make sure we understand for the thickness, how long we have to compact that. And there's some software packages that can kind of give you some ideas as to how long you have to compact that material, depending on weather conditions and the time of year. So when we go to sample our material, we have to look at something that's known as random sampling. And no matter how careful we are, we can introduce bias into the sample. When we say bias, we're not saying somebody's intentionally influencing the results, but just by handling that material, sampling it, we can bias the sample. So when we do random sampling, we're saying that sample can come from anywhere. Whereas if we leave it to our own devices without using a process to do this, we're more than likely going to take it when it's convenient for us. So our first sample would probably come first thing in the morning, because that's a good time, because, hey, I'm ready to go and I want to sample now. And then we would probably draw another sample mid-morning, maybe something right after lunch. But again, maybe that's not representing what's going on out there. And so we want to do a random sampling process so that every square foot of pavement or every ton of material that's produced has an equal chance of being sampled. Because when we do random sampling, we're trying to balance the risk between the people who are paying for the material and the people who are producing that material. Because when we look at it from that perspective, if you have one bad truckload of material that leaves a mix plant and that material doesn't meet the specification, but that's the only spot you sample, well, there may have been 80 other loads of material that left that plant that were perfectly fine. But now that risk is on the producer because we only sampled that one truck. And so we're going to characterize all 80 loads based on that one truckload. Likewise, if you happen to be the people paying for that, maybe that one truckload that you sample is really good. And then the other 79 truckloads are really bad. And so now the risk is on you that you're going to be paying full price for a material that is not what it's supposed to be. So that's kind of the idea here is that by randomly choosing when and where we're going to sample, that gives us some understanding of what's going on throughout the entire day. And we're not biasing it just because it's convenient for us. So how do we know when to take a sample? Well, we're going to talk about that a little bit more, but the specifications and the standards that we live by tell us how many samples we have to do. A lot of times it's based on tonnage. So every 400 tons, maybe you have to pull a sample, or 500 tons, depending on where you are. If you're coring, it's going to be however many tons go out there, and that kind of thing. And then how many samples do we need to take to represent that day's work? We're going to talk about that some more as well. So random sampling is really used to ensure fairness, to help eliminate the bias that's out there. And again, it's not intentional stuff that we're doing, but we all fall into easy patterns. And if you question that idea as humans, the first day you walk into a classroom and you sit down in a set of chairs, guess what happens the next day? Everybody goes and sits in the exact same chair that they sat in the day before. Why? Because we are predictable and we are biased and we tend to do things like that. And we don't even realize we're doing it. But it's kind of like, okay, on day one, you find your chair, and then you just, on day two, you go right back to the same exact spot. So that's an example where we are doing that, and it's just the way that humans are kind of hardwired. So we're going to use random numbers to make sure that the materials that were being sampled are not specifically called out for any reason. And that's going to help us to determine the sample locations or the loads and times that are going to be actually sampled. And this is actually a requirement by US federal code. That's part of the actual standards that we live by. And so the definition of a random sample is a sample drawn from a lot, and a lot can be an entire day's production. It can be an entire project's production, but that what we're assuming is that it's made using the same conditions and the same materials. So if something changes, now it's a different lot, and you would have to change that. And again, there's some jargon in here that's probably making your head spin a little bit. If you were to take a job and start working in this is something that would come to you very quickly when you start seeing it laid out in the field and that kind of thing. But a lot is we assume it to all be essentially the same material. And so we're going to draw a random sample from that lot, and that's going to be what we do and what we actually test. A sublot, we can divide the lot into smaller portions. So if let's say an entire project is going to be your lot, which is 20, let's say it's 20,000 tons of material, we can say we're going to have a sample that comes out of each sublot, and we can say the sublot's maybe 500 tons. So therefore, we're getting samples throughout that entire production run, but they're still randomly located so that we're not introducing bias into the sample because we decided that it was more convenient to sample it at 7 a.m. than it was at 8:30 in the morning or whatever it happens to be. So we use these processes to help minimize the amount of help to reduce the amount of variability we introduce into the sample. And so here's just an example showing you where you can divide a lot into sublots, and then a sample has to come from each one of those sublots. And the sublots are essentially the same size. And it's called stratified random sampling when we use sublots, because what we're doing is we're forcing a sample to come from each of these sublots, and therefore it is called stratified random sampling because it helps to spread them out. Because if we come back, so if we just did if we just sampled randomly in an entire lot of material and we wanted 5 samples, we could have all of our random locations fall kind of in one little area just because of the way that the random process works. And so all our sampling could happen right here, but then we don't sample anything else. And so, well, we have a good handle on what's happening in this one little spot. We don't really know what's going on throughout the rest of that entire lot. So that's why we like the stratified random sampling routine, so that this way here, it forces those samples to come from throughout that entire lot. And the random process, there is actually an ASTM standard for this, ASTM D3665, where we calculate random numbers. You can use, some places will allow you just to use the random function on a phone or a calculator. Some places have spreadsheets that are programmed to do random numbers, and then you would just put in how many tons you were going to be using, and it would help you to generate where those random numbers were located. But again, it is a random process. It's not just walking down the road and every third telephone pole you're going to sample. It is going to be a very formalized process to ensure that we're minimizing the bias that we're introducing. So if we wanted to do a random number calculation, we would take our random number and we'd multiply it by the sublot size, and that tells us where in that sublot we're going to sample. And usually we're going to reference it from the beginning of the lot. So you have to add the tonnage or the length from the previous sublots. So if you're sampling in sublot number 3, you have to add the tonnage for sublot number 1 and sublot number 2. So let's say they're 500-ton sublots. And when we did this calculation up here, this turned out to be 75 tons. So our sample in sublot number 3 is going to come at 500 plus 500 because that's the size of the sublots. So then we have to add the tonnage for sublot number 3, that's 75. So our actual sample is going to occur at 1,075 tons. So you have to add those previous sublots into it to be able to get there. And so here's an example. If we have a sublot length of 625 feet and a width of 12 feet, we would take, and we're going to, so we're going to divide this into 5 sublots. In this example, we're going to have 5 sublots. So to get to 5 sublots, we have 625 feet. We're going to divide that by the number of sublots. So each sublot is going to be equal to 125 feet. So yes, there is some math that gets used in these processes. So each sublot is 125 feet long. So we're going to take our sublot at 125 feet. We're going to multiply it by our random number, which we had before, which was 0.4873. And that gives us an answer of 60.9 feet within sublot number 3. But remember, we have to go through sublot number 1 and sublot number 2 to get there. So we have to add 125 feet for sublot number 1 and another 125 feet for sublot number 2. So therefore, that is 250 plus the length within sublot number 2, which is 60.9 feet. And yes, I can't believe my handy dandy writing here is going to be preserved and recorded forever. But it is. And so our answer comes out to be 310.9 feet from the beginning of that sublot. For width, it's a lot easier. We don't usually divide it into sublots. And so for width, all we're going to do is we're going to take our width, which is 12 feet. We're going to multiply it by the random number. And that's going to be 3.9 feet from the edge. And so, and we say designated edge. Some specifications tell you where to measure, which edge to measure from, whether it's the center of the road, the left edge, or the right edge. And we need to make sure we follow that and measure in the right direction, so that if somebody else comes back to look where you were, they can find the exact spot that you were. So I will unshare myself here, and Scott, you'll pick up from here.
We're going to talk, as I get this going, we're going to talk about now, Jim introduced how, to generate a location or a time or a truckload or something, random location for collecting the sample. And now we're going to kind of segue into physically collecting the sample. And the reason that we need to do that, as far as the loose mix collection, the reason that we have to do it, okay, is because we need to take it back to a lab, and that lab is typically at the production facility. We're going to compact it in order to simulate various conditions of it, specifically things like air voids. And we're also going to take the loose mix and we go through a burn process where we develop, it's a test that tells us what the actual asphalt content is of the HMA itself. And then we actually do a gradation as well. I know Jim and Alex, I don't know if I was here when you guys talked about aggregates. I might not have been present for that meeting, but nonetheless, we actually go back and it's this deconstruction process where we verify that everything that is in the mix is everything that was prescribed for the mix. And so that's why we physically collect these samples, okay, on site. and bring them back to the lab to run all these tests to make sure that we are getting what was paid for. And so we have to sample the loose mix. And in Connecticut, there's a requirement for that loose mix that it actually comes. It can't come from the plant. Now it has to come from the actual job site. And there's multiple different scenarios on the job site where we can actually collect that loose mix. And this first slide here, what you'll notice, this is John, who works in the CAP lab with us. And he's actually collecting that material off of grade, right, from just in what's called the wing of the paper. It's not the wing of the paper. It's called the auger that is advancing that mix forward before the screed runs it over on the paper. And so that's one application. And we're going to go through a number of different possibilities in Connecticut. Okay, and these are them. So we can collect material, the mix from what's called the hopper. Okay, there's a hopper on both the paver as well as the MTV or material transfer vehicle. And the hopper is what the truck that delivers the mix to the site physically dumps the mix into. Okay, that can exist on a material transfer unit, or it can exist on a paver if there is no material transfer unit. And that's a possibility. This is actually, in some states, this is a requirement to take it from that location. So for instance, if you ever go up into the state of Maine, okay, and you get on a paving project, you'll notice that for quality control, they are collecting the mix directly from the hopper. At least that's their specification currently. They're always subject to change. But right now, that's a requirement if you go to Maine. In Connecticut, it's a possibility. You have the option of doing that. The second bullet down is called the MTV chute. Okay, this is something that does happen periodically in Connecticut, and we're going to get into all these different scenarios. The third bullet down is the uncompacted paving mat. We have images of doing this from behind the paver prior to compaction, before the breakdown roller starts compacting it. And then finally, the auger, which you go back here, you saw the image of. This is called sampling from the auger. Okay, this is something that's very common in Connecticut on DOT projects. So sampling from the MTV or the paver hopper, what you're looking at here in this image, okay, is a paver hopper. So the truck that delivers the mix to the job site dumps directly on a project like this, dumps directly into the paver, or it might dump directly into the material transfer vehicle hopper, okay, that receives the mix. And so the way that this is done, there's some safety issues that we have to address first, because you're on site and you have haul units or trucks that are full of mix that are routinely backing up to the material transfer vehicle or to the paver hopper. And so there's a safety precaution that has to be taken, so there's not a pinch point. You know, the last thing we want is for somebody to get hurt, or possibly, you know, even worse than that, you know, when a truck backs up. And so we make sure that the trucks are stopped, and the paver actually has to stop, or the material transfer vehicle, whichever you're sampling from, actually has to stop. And then we're going to collect a minimum of 3 increments of this mix directly from that hopper. And so the way that AASHTO says to do this, okay, is to remove, we're going to create almost a vertical shelf, if you will, and you can kind of see that in this image here. And so we're going to remove the upper 6 to 10 inches of material from that pile. And then you're going to scrape down, okay, the front of that pile in the middle of the hopper area that you're facing, about 8 to 12 inches. And that's going to form that vertical face that it is desired that we collect our increments from. And we're going to collect a minimum of 3 increments by inserting our shovel, shoving our square shovel directly into that face. And we're going to obviously deposit that material into buckets and then thoroughly recombine those increments for our field sample. Okay, and so this is one option that is allowed through AASHTO R47, R97 for the collection of mix. That's a slide here. Another option that we have, and I mentioned material transfer vehicle. On the left-hand side of this picture, what you're looking at is a paver, all right? And so that paver, or you see the word Weiler on there, that has what's called a paver insert. Now, on a job like this, where there's a material transfer vehicle that's depositing material into that paver hopper, it would be impossible to stand in front of it and collect mix out of it with a shovel, because it's way too high in the air. And so in any case, what we have the option in that case is, if we wanted to collect from a hopper, we would have to take it out of the hopper from the MTV, or we can actually take it from the chute, if you will, from that material transfer vehicle, in which case we would have a wheelbarrow or some sort of a large receptacle. And let me see if I can get a highlighter here. stand by. Generally, I'm depending on Alex to do this. There we go, highlighter. And so this is the chute, and this is the you know, the boom here. And so what we're looking for is we would have the operator kind of swing that boom over to the side, and that would deposit material directly into whatever our sample receptacle is. And typically that's going to be some sort of a wheelbarrow, but it could be any sort of a chute, maybe on the back of a pickup truck, or what have you, to completely interrupt the flow of that material as it comes out of the discharge comes out of that chute itself. And so that's another option that we have when we're on site collecting this loose mix. Another option that we have in accordance with AASHTO is sampling directly from the uncompacted mat, and that's what's going on here. We collect a minimum of 3 increments off of the mat. Okay, we dump those into our buckets, and then that material gets thoroughly recombined for our field sample. So this involves a little bit of coordination because it has to happen prior to the application of the breakdown compaction unit, so what's called the breakdown roller. We've got to make sure that it happens directly after paving, but prior to breakdown, where we fill up our buckets. And then somebody has to come through. Somebody has to be responsible for coming back through with some hot mix to fill in those holes that we left by digging into the mat. Okay, so this is another option that we have. The most common options that you're going to see in Connecticut with respect to sampling mix, okay, directly on from the paving project, all right, are going to be collecting material from the auger or collecting material from the material transfer vehicle itself. Okay, in Connecticut, we have a requirement where it's applicable that we have to use material transfer vehicles, and so sampling directly out of the hopper of a paver would be, you know, virtually impossible on most paving projects. The idea when you're sampling from the auger here, now you've seen a couple of videos in past classes where the paver is advancing. You know, the paver has an auger and then a screed, and the auger is advancing the material forward and out to the screeds as the paver advances forward. And so what John is doing in this picture is he's laying his shovel directly on grade, and that pile of material is being advanced forward. And as soon as it covers his shovel, he's going to lift as vertically as possible. Now that's a hard thing to do, but as vertically as possible, straight up through that pile and deposit that material into the bucket that he has right there, ready to go. All right. And so he'll keep doing this, and it's more convenient to have 2 people with you for somebody to advance the buckets, you know, as you're shoveling into them, because this is a mobile operation. The paver is moving when this happens. And so it's much easier when you have 2 people involved. Okay. And so those are the options that you have for collecting the mix. Now, when we collect mix, there's quite a bit of it, and it needs to be broken down into portions so that we can box it up, and the different boxes of material go to different places for testing. And so once we have that material, we have in Connecticut, it's required that we use this splitter here. This is called a quartermaster, and you see that's actually got a label on it that says quartermaster. This HMA material that gets collected on site, now that we've collected it, needs to be broken down into test size portions, right? And there's a requirement for the way that that's done. We can't just shovel some into some boxes and pass that one off, and shovel some into another box and pass that off. It's got to be done in a uniform manner. And the objective, when we say splitting the HMA samples in the field, the objective here is that all of the split samples are going to have the same continuity, the same uniformity. And so if we test one box versus another, you know, ideally we would have split them in a manner that they would have results that would be repeatable, right? That would be identical, hopefully. And so there's a uniform process that we have to follow. And in Connecticut, we use this splitter. It's called a quartermaster. Okay. And so if you look at the quartermaster, before you put the hopper onto it, it's got 4 chutes. Okay. And underneath each of those 4 chutes, we're going to use some sort of a sample receptacle. In this image, they're using buckets. Okay. So I'm going to change that here. Excuse me 1 second. Actually, going to change to a laser. All right. And so that's what's going on here. Each of these chutes is going to deposit material, okay, into one of the 4 containers that exists underneath it. Over on the right-hand side, there is a hopper. This is what the bucket full of collected mix gets dumped into. And it has what basically like a trap door. It says it has a release mechanism. There's a two-part door, okay, that exists, and you're looking at the back side of it, but over here on the right, you can kind of see the handle to it. That is basically like a false floor. So that locks up to hold the mix. Okay, so we can finish it off at the top, and then we release that, and that deposits the material evenly, hopefully, and uniformly into each of those 4 sample receptacles underneath the splitter itself. Now, with repeated use of these splitters, this is a nice clean setup that you're seeing in this image, but with repeated use, the asphalt tends to build up on the chutes and the hopper and the buckets and everything. And just like everything else that we use with respect to hot mix asphalt, the asphalt tends to build up on it. And so it's a good idea to keep it clean. Okay. And so we can use a non-petroleum based release agent, okay, to help keep it clean with each application. And that's what's going on here with respect to the application of that release agent. And what you'll notice down here in this area is each of those flaps that exist, like I said, it's a 2-part door. Those get raised up and locked into place, okay, with this mechanism here. When we're ready to go, after we've dumped our material in there, we will flop that lever over, that releases the door, and that material, okay, then gets deposited over those 4 chutes and into the sample receptacles. Okay. So we have the option of using sample boxes as well. It's not just buckets that can be used for receptacles. And that makes sense because in Connecticut, the mix actually gets boxed up prior to being sent to wherever it's going to get sent to. And we'll talk about that in just a minute. Okay. And so we put the splitter down and make sure the chutes and the chute walls and the hopper and everything are all clean. And we're going to raise up the floors and lock the floors so that they're closed. We deposit all of our material into this hopper here. And once everything's set and we have our sample receptacles set underneath the splitter, then we're going to release that lever right here. And that drops each of those doors down. And hopefully, to the best of this unit's ability, it's going to drop that material and uniformly distribute it into each of those sample receptacles that exists underneath that splitter. Okay. Now, in the event that further splitting is required, the way that AASHTO R47 says to do this is you're going to take 2 of these diagonally opposite receptacles and return them to the splitter hopper, okay? And you would repeat this process until you're down to what is called your required sample size. In Connecticut, for the way that things are done for splitting, specifically for the requirements to meet Connecticut DOT requirements, generally that's not going to be an issue because it's a significant, a pretty, I should say, substantial sample size that is required. Okay, it's a minimum of 4. I think we have a slide on this of 14,000. Yeah, here it is. Next slide. Perfect. We have a minimum of 14,000 grams per box. That's a significant amount of material, and so typically further splitting is not generally required. But if in the event that were to happen, you would split it exactly in half and then repeat that process. Okay, and so in Connecticut, what's going to happen is we're going to end up with 4 samples, okay, from that split. And each of them are going to get taped up, and they get taped I should say sealed with that security tape that's provided by somebody from the DOT that is on site. And there's going to be 4 boxes, okay? One of those boxes gets taken back to the facility, and it gets used for testing for volumetric purposes. And when I say that, I mean things like air voids. There's going to be one of the specimens that goes to generate a gyratory specimen. Okay, so it's going to get compacted in the super pig gyratory compactor. Part of that sample is going to be used in the ignition oven to determine what the actual asphalt content is. And then there's going to be a sieve analysis or gradation done on the material that has had the asphalt burned off of it. So there's a lot of stuff that takes place with that collected loose material. The other 3 boxes, they contain the same material. One of them gets kept for a potential dispute resolution, okay, which is part of the QA process in case further testing down the road, if there's ever a dispute as to the quality of the material and ultimately payment, that would be reserved for that. There's also another box that gets used for what's called assurance. There's potentially an assurance that gets run on some of these various mixes. One box gets reserved for that, and another one gets shipped off to the Connecticut DOT for testing at their laboratory. So there's 4 samples that come from each one of these splits, and each one has its own intention. Okay. So this, I'm going to show you a video. This is the actual split process. I'm going to given the time, let's see, I don't want to go over here. We have a couple minutes, a few more minutes left. I'm going to show you this video. I'm going to reduce the sound and just kind of narrate over the top of it, I believe, if I'm not mistaken. This is a lengthy video. Yeah. Okay. And so this is just a video right now that's showing you. So this is the paver that is advancing down the roadway. And this is an example of collecting mix from the paving auger. Now, there's two different ways this is done. They had some safety in mind. This is not a bad option. They stopped the paver. The paver is not always going to stop. It depends on what's been coordinated on that paving project. But you see the auger here that is advancing material forward prior to it being sampled. Okay. And those sample buckets are the receptacles that we're going to use. And ultimately that mix is going to get brought over to the splitter. Okay. So this is an example, like I mentioned, this is very common in Connecticut to get mix that is sampled directly from the paver auger. Advance this a little bit. Okay. That gets brought over to where the splitting is going to take place. All right. And so there's the splitter on the bottom. Jim, is this coming through okay? Is that actually playing?
Yep,
okay.
it's fine.
I want to make sure it's not too grainy or broken up or anything like that. Okay, so that's the chutes are here. Let me get my, I think I can use my laser here. Yeah, that's all right. In any case, so they're going to get, there's a non-petroleum based release agent. So everything doesn't stick. Then they're going to put the hopper on there. They're also applying release agent here. Okay, and those doors are going to get locked shut. Okay. And now each of those buckets are going to get deposited into that hopper. And that's going to hold the material. And so the idea, again, is by the time we have these 4 splits, right, that they're going to all have a uniform consistency to them, meaning that, you know, I should be able to take one box or another box, or you could take a box or whatever. If we compare results from testing, they should all have the same properties. And that's the idea behind the utilization of one of these mechanical splitters, is that all of the split samples are uniform. So that's a material that is as it exists in the splitter hopper. Okay. And now the trap door is going to be released. That's that lever right there. And that drops the material, okay, deposits it evenly, okay, into those buckets or those receptacles underneath. Okay. Let's see, I'm gonna kind of advance forward here. I think we have some of the boxing up. Yeah, this is just cleaning the splitter, which is necessary, and just further splitting here. All right, and this is showing them dividing up those materials that are split into those receptacles into boxes that are then going to be that are going to be taped with the security seal from somebody from the Connecticut DOT. They're going to get labeled. And again, one of those goes back to the Connecticut DOT Central Testing Laboratory. One of them gets used for testing at the facility, and 2 of them get kept, one for assurance testing potentially later on, and another one for potential dispute resolution. Okay, going to advance here. Okay. And so that is sampling loose mix as well as splitting loose mix for future testing. And again, just as a reminder, the reason that that's done is because we need to routinely be able to collect and assure the contents of the material that's going down into the field. Okay, so whoever's, you know, cutting the check for that particular project, which is generally a hefty amount of money, wants to verify that they're getting the correct amount of liquid asphalt binder, that the gradation of the aggregates is actually what is, you know, that it meets job formula requirements, whatever has been submitted and accepted for that project prior to its construction, and all the other volumetric requirements that might be part of that as well. And so that's the reason why we collect this mix, and we want it to be uniform. We want each of those samples to be completely uniform, and that's why there's a standard uniform procedure for being able to split those materials as well. Now, another form of sampling hot mix asphalt is actually collecting density specimens from the field. And that is obtaining cores. There's a separate AASHTO designation for this. That's AASHTO R67. And the reason that we would want to cut a core from the roadway and then measure its density is because density, through all the experience that we have, is directly related to the strength of the asphalt mix itself. Okay, it tells us we can derive from density the amount of air voids that we have compacted into place. And it's also a good indicator of final strength. So for instance, if we have something that is very under compacted, we can probably expect that roadway to fail, a lot sooner than what we would expect. And so we want to make sure that we are compacted to a certain degree of compaction. And so that's what you're seeing here is an image of the collection of a core that's from a compacted pavement after construction that is going to be obtained and then brought back to a testing facility so they can physically measure the density and ultimately air voids of that mix. Okay. And this is pretty much, okay, there's a couple different clauses on here. And the one thing, if you find yourself ever cutting a core and handling a core or doing anything with a core, it's important to note that the extraction of a core and the handling of it afterwards, there's nothing that we can do that's going to improve the condition of it. The only thing that we can do is to detract from the continuity of that core. So it's got, every time you look at a core, it's as good as it's ever going to be. It's never going to get any better, right? We can't take any air voids out of it. We can't further compact it or anything. And so the way that we cut the core and the way that we handle the core afterwards is really, really crucial. Right, we want to make sure that we're not ripping these cores out of the ground after the cutting and so forth, that we're letting the coring bit do the work, and that during handling and transport to the testing facility that we're not causing any damage, that they're not bouncing around in the back of a truck or in a box, and so forth. And so it's important because the numbers that are associated with these cores have an awful lot of dollars and cents. There's a great deal of money associated with the testing results from these compaction specimens. When we're cutting a core, there's some PPE that is required. Okay, it's loud. There's going to be a generator, there's a cutting apparatus, the drill and everything. And so you're going to want both hearing and eye protection. If you are in the vicinity of, or if you're actually cutting the core yourself. Okay, high visibility safety apparel. Anytime you're around or near or in the roadway itself, it's a requirement that you wear high visibility safety apparel. Okay, you should have closed-toed shoes, full-length pants. Okay, all of this stuff. Basically, whatever your company or whatever your agency requires of you, you should be wearing. The core drilling machine, that's exactly what we said. These machines are drills that can either be mounted on some sort of a portable frame, which is what this is here, what you see. They can also be mounted on trailers or on trucks. There's a lot of different configurations of different types of coring rigs that will show up on paving projects. Okay? This one that you see here is portable. When the core is done and when that core is done being cut, then that coring rig gets thrown, I shouldn't say thrown, put back into the truck. It's put back into the truck and moved on to the next location or taken back to the shop and so forth. And so there's a drill that's mounted on that frame. Okay, and then this barrel, this yellow tube that you see here, has diamond. There's carbide, it's combination of carbide and diamond teeth that exist at the bottom of that are used for cutting through the asphalt pavement, right, to get us the core that we're looking for. Okay. Once we cut to the desired depth, core retrieval is not always as simple as just reaching down and picking up the core. It can be pretty tricky to get them out. And again, the whole idea is that we pull those cores out in a manner that is not going to induce any damage. We don't want to cause any damage to that core because we want to use it for measuring density. And if we cause any damage to it, that's going to decrease the density. Okay, and that's going to cause problems. And so there is some acceptable retrieval devices. The use of wire is pretty good. Over on the right-hand side, what you'll see, if you have to cut a full depth core, a straightened bucket handle is what you're looking at there. That's one of our favorite tools at the Cap Lab. We use those frequently on coring projects. In the middle here, okay, that blue device, if you're cutting a core and you want to perhaps break it off halfway or you want to retrieve it in a manner that's going to minimize the amount of damage done. This is a tool that's made by a company called Humble. I'm sure other manufacturers make them now too, where you insert that barrel over the top of the core that you've just cut, and you would tighten up this nut on the outside, that bolt, I should say. Okay, and that's going to squeeze the core. So when you handle that unit from the top, it's going to cause a lot less damage during the extraction of that core. Some no-nos here. So if you had something like a drift punch, or a sharp flathead screwdriver, while it might be handy and, convenient to grab it and try to wedge it down in between the core hole and the core itself, those types of items are sharp and they tend to damage the core, particularly on newer pavements where the pavement is still, somewhat pliable. That's going to cause damage. And so those are not really desirable tools to use. In addition to the correct tools, we want to make sure that the pavement is cool enough to be able to cut and extract the core without causing damage. And so the way that we do that, if we have to, is with the use of some sort of cooling material. Generally speaking, that's going to be ice. Okay. Ice, if you take a bag of ice, you can either put a pile of ice on the area where you're going to cool it down or just throw the bag directly on top of the pavement. There are companies that will use something like dry ice. Okay, there's a company out in New York called Advanced that uses dry ice frequently. But nonetheless, we need to cool that material down before we cut it and extract the core. Right. And once the core is extracted, once we hand it off or get it back into the lab, we want to know where it came from. We want to know exactly what project it's from, what location within that project, lot, sublot number, date, material, all that stuff. And so whatever the pertinent information that is necessary, that needs to be labeled on the core itself. Okay. And as far as suitable packaging equipment goes, we want to make sure that we're not damaging that core. So it shouldn't be thrown in the back of a truck. It should be cushioned, okay, and protected from extreme heat and bouncing around and so forth. We want to make sure that when we extract it, it maintains that same continuity from that point until the time it's actually tested.
So at this point, Scott, it's just about 11. It's just about 11.
Okay.
So what I would say is, why don't we stop here?
Okay.
We'll finish these few slides up next week. I don't mean to cut you off, but I
No,
know
that's
that
fine.
everybody has to get to the next class. So,
Right.
so we will pick up with this coring next week. I know there's only a little bit left, but we will run late. So with that, if anybody has any questions, we're happy to answer them. But I know, like I said, usually the bell is ringing and it's time to start moving on to the next adventure.
Yep.
And you
Okay.
can also email me any questions as well, and go ahead and take quiz 4. And if you have any questions on that, feel free to email.
Yep, and we've covered all the material for quiz 4, so there's nothing
Perfect.
on there that was not covered.
Awesome. All right, great. We will see everyone next week. Thank you, guys.